Alright, welcome back to my YouTube channel. I'm Xavier Smith. Today I'm going to talk all about probability. So listen up and let's get started. So the common example of probability is flipping a coin, right? So you'd say, okay, what's the chance of getting heads and what's the chance of getting tails off one flip, right? Well, you'd be like, it's 50-50, right? 50% chance you get heads, 50% chance you get tails. But what's the chance you get two tails in a row? Well, then you'd say, okay, it's a like 1/2 chance to get tails, right? It's a 1/2 chance to get heads. But the chance to get tails in a row, it's not like, oh, I just got tails, so now it's like a 75% chance I get heads. No, coins do not have memory, which is really important here. Because this coin, I can flip it and I can get heads 10 times in a row, but the chance that I get heads again on the next flip is still 50% or 1/2. So that's important. If this does not have memory, the chance of getting like a head is just 1/2 times 1/2 times 1/2. But if this coin did have memory, if it was like I was picking names out of a hat, right, and not replacing them back, or like picking cards out of a deck and not replacing them back, it's like, okay, what's the chance of getting spades once, right? Well, that's 1 out of 13. What's the chance of getting 4 spades in a row? Well, that's 1 out of 13. Well, what is it? 1 out of 13 out of 52, right? The chance of 1 spades. Then it's 12 out of 51 because you took that 1 spade out of the deck, so you take it out of the numerator and denominator. So 12 out of 51. Then times 11 out of 50. Then times 10 out of 49. And it keeps going for as many spades as you want. So here, where there's no replacement, we're just saying, okay, the chance of getting heads once is a 1/2, but then the chance of getting heads again is a 1/2 times a 1/2, right? Which is 1/4. So the chance here is 1/4. Then the chance of getting heads then tails, again, is 1/4. Chance of getting tails and heads is 1/4. The chance of getting tails and tails is 1/4. And what you realize is here, 1/2 plus 1/2 is 1. 1/4, 1/4, 1/4, 1/4 equals 1. So here is our little probability model. And at every step, all the probabilities will add to 1. And all of the probabilities are between 0 and 1. 0 meaning this will never, ever happen. 0.001 means this could happen, but that is so rare that it almost never happens. 1 being it happens all the time. And then like 0.5 would be in the middle saying like, oh, coin flip, heads or tails, 50% chance. So a complement, you'd say, okay, like what's the chance of not getting heads on your first flip? So you'd say, okay, P is the probability. And then we're saying, okay, heads, A. So if you just had the probability of A, right, the probability of getting heads on your first flip would be 1/2, right? But the probability of not getting heads would be, you put this little A to the C, so the complement. And all that means is 1 minus the probability of getting heads, which is 1 minus 1/2, which is 1/2. Clearly, it's an easy example here. Then mutually exclusive. That just means if there are these two events, right, you can't get heads and tails at the same time. So they are mutually exclusive. And that means if you're saying, okay, what's the chance you get this or that, like P, A, or B, you're just saying that's the probability of A plus the probability of B. But here, if you could have two things happen at once, right? Like if these two events could happen at the same time, you'd say, okay, well, like you're saying, like how many, like do you have dogs or cats, right? 13, say they have dogs, like 13D, 14 cats. Hey guys, 5 a.m. me talking because my mic cut out on the rest of the video. So I'm just going to take over from here. So we're saying there's 13 dogs, like people with dogs. There's 14 people with cats, and there's 10 people with dogs and cats, right? And we're going to say there's 20 people. So if you wanted to make this into a diagram, you could use one of these Venn diagrams. It always looks like this. So we're saying, okay, there's 10 people that have dogs and cats, right? This is dogs, this is cats, this is both. There's 10 that have dogs and cats. Then there's 3 that just have dogs. So here there would be 3 that just have dogs. Here, there would be 4 that just has cats. And then here, there would be, what is this, 17? There would be 3 that don't have anything. So if you say, okay, what's the probability of someone having a dog or a cat, right? You're like, okay, well, it's 13/20ths plus 14/20ths. But you get, what is that, 27/20ths, right? And that's more than the people we have. So what you have to do here, when these are not mutually exclusive, clearly here, coin flip, you can't get heads and tails, mutually exclusive. But here, you can have a dog and a cat. Like, having a dog doesn't mean you can't have a cat, except if your dog's really ferocious and it's gonna like eat the cat, or your cat's gonna eat your dog. But I haven't heard of that happening yet. Um, 13/20 plus 14/20, you're gonna have to subtract out this intersection. So you're gonna say minus 10/20, and that would give you 17/20. And that's exactly true because there's 17 people in here, and there's 3 people that don't have it. So exactly, 17 out of 20 would be your answer. Okay, so that's mutually exclusive. Now, the probability of A given B. So here, you're given something. You're saying, like, okay, what's the probability of getting heads given that we just got tails, right? Or, no, this is the probability, because we said B was tails. So this is the probability of getting heads given that our first, like, flip gave us tails. So this whole other part doesn't matter to us anymore up here because we were given that we had tails. So it's not the 1/2 chance to get tails. No, it's we have tails already. Now, since we're at tails, what is the chance of getting heads? Well, the chance of getting heads from tails is still 1/2. Even though here it says a fourth, it's still half a chance to get it. So what you're trying to say by given is you're shortening, like, the sample. You're like, here you had four coin flips, right? But when you're saying that you start off with tails, then you only have 2 coin flips, really, because these 3 are all, well, these 2 are all gone. And then you only have these 2 coin flips, and you're saying, okay, it's a 50-50 chance to get either, so it's 1/2. Okay, now let's put everything together and put it all into a more complicated but real world example. Okay, so 22% of these patients that walk into like a minute clinic have the flu, right? They are incorrectly called negative 3.7% of the time. And then for the people that don't have the flu, they are told they are incorrectly positive for 2.6% of the time. So what we do here is we say, okay, these are the patients, right? This is one, really, it's everyone. And then we're like, okay, I'm going to denote flu as F and no flu as flu complement. I know that seems counterintuitive. You'd be like, I want the ones that don't have the flu to be the normal number. I do too, but I'm just going to do it like this. Because flu complement just means all the people that don't, yeah, means all the people that don't have the flu. So 2.22 have the flu, right? And then if we take the complement of that, we can find who doesn't have the flu. So that would be 0.78. It would be 1 minus 0.22, which is our formula for complements. Also, not sure if I mentioned, but like with a coin flip, you could get heads 10 times in a row, right? But over time, if you flip a coin 10,000 times, it's likely you're going to get very close to 5,000 heads, 5,000 tails. So in the short run, probability is really janky, right? Your answers may not make sense because you're like, the chance was 1/2 and I got heads 10 times in a row, right? How did that happen? Well, over time, probability, like if it's real probability, it'll flatten out to its estimated probability. So by like 10,000 flips, you might have a 51-49 probability or a 50-50, but you're probably not going to have like a 60-40 probability. But here in the short run, if you flip 25 times or 30 times, you might get like 21-9. And you're like, well, this doesn't make sense. And it's like, because you didn't do enough trials. So just do a ton of trials And when you're explaining things, you're going to say down here, I'll tell you, it's like you use the word many trials. You have to do so many trials for these probabilities to line up. Because if you just do a trial with like 10 people, it's not going to line up. Okay, now we know that the amount of, we're going to say this is positive result, this is negative, this is positive, this is negative. Okay, so these patients that have the flu are incorrectly told they're negative 3.7% of the time. So here that would be 0.037, right? Then they are told, like, the ones that are positive, well, the ones that don't have the flu are told they're positive 2.6% of the time, so 0.026. All right? Now, what you're going to do is to find these other ones. You're not going to say 1 minus 0.037 because then all of these in one row aren't going to add up to 1. They're going to add up to more than 1. You're going to say, okay, this is sorry, what did I do here? Never mind. Let me show you something that I did wrong. So you're going to multiply by those numbers, but you're not going to put those numbers there. So 0.22 times, there was negative 0.037% of the time, 0.037, right? So we are going to get this number that is 0.00814. That does not look enough like an 814. All right, so you're going to multiply the probability of someone not having a flu by the probability that the probability someone has the flu times the probability that they still get a negative result, right? And you're going to put that here. So again, it's like this and this, you just multiply the probabilities, multiply across. So here, you're like, what do we multiply 0.22 by? Well, we were told that these people were like 0.037% of the time, they were negative. So that means that the positive is the complement of that. So 1 minus 0.37 would give us 0.963. So these people are told they're positive 0.963% of the time. We have to multiply that by the probability they are, like they have the flu already, and you'll get 0.21186. I'll write down the calculations for this next one. So there's a 0.78 probability that people do not have the flu, right? But there's a 2.6% of the time chance that they still get a positive. So this will be 0.78 times 0.026, just multiplying the probabilities. All right, so 0.78 times 0.026 will give us 0.02028. Now, the chance of getting a negative for these people would be 1 minus 0.037. We're finding like the complement. Well, 3.7% of the time it's negative. Then what percent of the time is it positive? It has to add up to 1 there. So this would be 1 minus 0.037. That would give us 0.963. And then if we do 0.963 times the probability they don't have the flu, 0.78, this would give us that's not right. This would give us 0.75114. And if I add all of these together, they should equal 1. So here our probabilities equal 1. 0.22 plus 0.78 equals 1, right? Here in each of these, the like percents, like this was 2.6% of the time, and then this was, on the other hand, 97.4% of the time, right? And same thing. These will add up to 100% or 1. The probabilities of these both occurring for this. And then here, all of these should add up to 1 in the end. So let's do it. 0.2028 plus 0.21186, I already added that one, plus 0.00814. And as you can see, it's like 0.99 something. So it's really close, right? Yeah, 0.991. So I'm right there. I might have had some rounding error somewhere, but that's honestly all right with this. If it at least rounds, you're good. Okay, so now find the probability that a random patient gets a positive result. So this is the probability of, let's say, positive equals, well, here is the probability of someone getting a positive, and then here is the probability of someone getting a positive. So if we just add them together, we'll get the probability of anyone getting a positive result. It doesn't mean they actually have the flu. It just means they got a positive result. So we're just going to add these two together. 0.02028 plus 0.21186. So this is flu and positive, and this is no flu and positive. So we're just adding those probabilities up. And this will give us 0.23214 probability. So if you needed to interpret this, you'd say, like, in this clinic, after many like patients come in, a random patient has a 0.23 like 2 probability of getting a positive result on the flu test. Something like that. Say say random patient, then you're going to throw in this probability saying they have this probability of doing what? Of getting a positive result. Okay, so now 4 patients are at random, right? And give the chance that at least one of them gets a positive result. Well, here, your formula is going to be like P of at least 1 is going to be the 1 minus, so the complement of none. Because, well, here you have discrete variables. So the probability of none means they all get negative results, right? But the complement of that, like anything that's not all none, means at least there's 1, right? That's just the logic here. You're like, you can get 0, 1, 2, 3, or 4 patients with a positive result, right? So just take out the chance where none of them get a positive, and you're good. Okay, so the chance none of them get a positive would be, let's find the chance that they do, let's find the chance they get 1 negative result. So this would be 0.75114, this is negative, and then this is negative, plus 0.00814, and that'll give us 0.75928. Then, again, we're saying like the probability of 1 coin flip, right? Heads is 1/2. The probability of getting a heads again is another 1/2. So it's a 4th to get 2 heads in a row. So here, it's the same thing. The chance of getting someone that's negative, like result, is 0.759. So you just multiply that by itself once, and you get the chance you get 2. Then you multiply it by itself again, and you get the chance you get 3. Multiply itself one more time, you get the chance you get 4. And that'll be 1 minus 0.3323 something. Minus, it's 1 minus that, and you'll get 0.6676. So there is a 0.6676 that if you have 4 random patients, there's a like 0.6676 probability that at least one of them gets a positive result. Doesn't mean they actually have the flu, just means they got a positive result. Okay, so given that they have a positive result, give the chance they are actually positive. Okay, well, we're like, find the chance that someone that has a is positive gets a positive result, and then put that over the chance that they are that they got a positive result. Okay, so here I just have to write it down first. The probability of someone being positive, right? Positive versus given that they have a positive result. Okay, so here we know everyone that has a positive result, right? So we can put that on the denominator, 0.23214. Now, just find the proportion of that are people that actually have the disease. Well, here, this is they have the flu and they have the positive result. So we'd put that 0.21186 and just divide them. equals 0.9126. So, given that someone has got a positive result, there's a 0.9126 probability that they actually do have the disease. So if they asked you for like the inverse of that, given positive result, what's the chance they don't have the flu? Well, that would be like 8.9%. Okay, well, 0.8089. I hope this video was super helpful. Sorry for 5 a.m. me. I did not want to introduce that on you, but gotta do what you gotta do when you have a test this day. Gotta get the video out. So thank you so much for watching. I really appreciate it, and I hope to see you again soon.